The last topic we're gonna talk about is a little bit out of place, like I said before, because it's about light ray, that's true, but it's actually about interference of light. And you might ask, like, why didn't I talk about this when we talk about interference of wave way back? Probably last week, I think, right? Is well, I don't know why. There's no good reason to talk about that here over back then. But the thing is that um, light wave has a very small wavelength, and that's gonna change things a little bit. The physics behind it is the same, but there's some approximation that we can do, which applies only for light wave. Okay, so that's why I didn't talk about this when we talk about interference of other wave, sound wave or something like that. Okay? And it's also probably good to kind of revisit that, kind of remind ourselves what we talked about last week. So what is this thing? Well, let's remind ourselves, like I say, about interference of wave in general. Like if we talk about like two speakers like this, S1 and S2, and you probably somewhere here, and then speaker 1 and 2 will give out wave. In this case, might be sound wave, right? And then our question is to ask whether the interference happening at point P is going to be constructive or destructive, right? So we talked about this problem before, and we know how to solve it. The way we solve this problem is to look at what we call the path difference, PD, and it's defined to be the line joining S1 and P minus the line joining S2P. Right, this is the path difference. Again, this is nothing new. You have seen this before. If the path difference is multiple of lambda, including 0, so 0, 1 lambda, 2 lambda, 3 lambda, then you have constructive interference. If you have half multiple of lambda, then you have destructive interference. We covered this already. Again, nothing new here. This is true for any kind of wave. Okay, hear me say it again. This is true for any kind of wave, meaning that if we talk about light wave, talk about sound wave, talk about wave in water, you just look at the path difference and then see whether it's multiple of lambda or half multiple of lambda to say whether it's constructive interference or destructive interference. Okay, that's good. But now let's talk specifically about light wave. So for light wave, because lambda is usually very, very small, usually very small. How small it is? Well, some of you might know from whatever your high school science class that the light, or especially visible light that you can see, the wavelength is in the range of 400 to 700 nanometers. Nanometers is 10 to the minus 9 meters. So in terms of meters, we are talking about 0.0000004 meters. Right. So it's so small that this is not something that you see in real life. Your hair is about a few microns, and that's about this digit here. So how thick the hair is, the wavelength of the light is about 1,000 times smaller than that. Okay, so you cannot see it for sure, especially things which is this small, right? But your eye is sensitive to the light wave, which is the wavelength in this range, right? So because the wavelength is very small, most of the time when we talk about the interference of light, okay, the two light sources, light speaker, that's a really good term to use, right? But a light source or a speaker for light, if you will, right? They have to be very close to each other for the interference effect to be detectable, visible to normal measurement. Okay, so most of the time we do this by using what we call a double slit. And again, the reason behind the necessity of using a double slit is just from the fact that the wavelength of the light is just so freaking small. What is a double slit? I'm gonna show you the picture first, maybe here. A double slit is actually just two holes very close to each other, and one hole gonna act like one source of the wave, so that's gonna be S1 here and S2 here. So it's like two speakers, right, for light. Again, similar to the two speaker for sound wave, right? So you have two light sources, S1 and S2, and in order for us to see the light, usually we put a piece of paper and use that as a screen, okay? And then you're gonna see light which can be bright or can be dark on that screen. And that's what is being drawn here. So it's a little bit confusing, but this graph here shows the intensity on this screen, okay? It's the intensity on this screen, right? So if you look at the screen on a piece of paper, it's gonna look something like this, right? So it's gonna be a bright stripe or spot on the screen or dark spot on the screen, okay? And this graph here tells you the intensity at different position on the screen. For example, at 0 here, the graph is largest, so that means it's the brightest in terms of the light intensity on that screen. Okay, so this is what this graph means here. And then as you go up, right, so at the center, right at the center where the number 0 is, right, how do you know that this is brightest, meaning that it's the constructive interference? Well, again, it's the same thing that we did before. You look at the path difference, which is the difference in the distance S1 to P and S2 to P, right? So these two lines give you the path S1P, S2P. You subtract them, that gives you the path difference. And at the center, the path difference is 0. So that means you have constructive interference. But as you go up along this screen or a piece of paper, maybe somewhere here, right, you can see that now the path to S1 is going to be a little bit shorter than the path to S2. So the path difference is no longer 0 in this case. So the path difference is going to get larger and larger when you go up, right? And then depending on whether the path difference is multiple of lambda, that means you get bright spot, which is constructive interference that happens here, 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 right? All the numbers are. That's constructive interference. So the path difference is multiple of lambda in these cases. Or you can have the path difference to be half multiple of lambda, which is the green position here, where you see the dark spot. So far, nothing new. It's the same physics that we had before when we talk about interference of sound wave, right? To see whether you get bright or dark spot on the screen, meaning that you see constructive interference or destructive interference, it depends only on the path difference, whether it's multiple of lambda or half multiple of lambda. So everything is fine. The only thing which is different is the following. because the distance between S1 and S2 has to be very, very small, right? Otherwise, you don't see the interference. It's just because the light wavelength is so small, right? It's kind of like a technical reason, if you may, but that's usually the case. Okay, so S1 and S2 is usually very small. Normally, we're gonna use the parameter D to indicate the distance between the two sources. D is sometimes called the slit distance. Okay, it's a double slit. Slit means hole, right? So it's the distance between two holes, and that's what we call small d. Usually, small d is less than 1 millimeter for this interference to be easily observed in real life. Okay, so that's very small distance d. And then what I'm gonna say next is because of this smallness of d, we can write down some approximation that applies only for light wave. Okay, so what are we gonna do? Let's look at this particular point here for no reason. Okay, I just pick randomly. How do we figure out whether point P is constructive or destructive interference? We have to look at the path difference. So the first path is from S1 to P. The second path is from S2 to P. And we have to look at the difference in the length. And you can see that the green one is a little bit longer, right? So the path difference is not 0, that's for sure. And you see now that because D is so small, right, these two lines are almost parallel to each other. They are not. Strictly speaking, they are not parallel to each other, right? Because otherwise they cannot intersect here, right? Parallel line will never intersect. You know that from primary school geometry, right? But this distance is small enough so that if you zoom in closely, these two lines look almost like they are parallel to each other. That's the main important point here, that they are almost parallel to each other. It's almost parallel to each other such that if we say they are parallel, we are not wrong by much. Okay, so that's the approximation we're going to do. So what does it mean for these two lines to be parallel? It means that the only difference in the length between two parallel lines, so I'm going to go back here and draw because it's easier this way. Again, I have two slits and I have two holes. One here and the other one, let's say here. Okay, it's very small hole. Again, I'm just zooming in so that it looks big like this. And remember that we zoom in close enough such that the two lines from S1 to P and S2 to P, they are almost parallel to each other. So that when we say they are parallel, we are not wrong by much. Okay, I'm just repeating what I said earlier. So I can draw the line like this. And I draw it such that they are parallel, which is wrong, but not wrong by much. Okay, so what do we have here? Because they are parallel to each other, how long is the red one compared to the blue one in terms of the length? Well, if you draw the line which is perpendicular to both lines like this, the difference in the length is just this section here, the green section here. Because the rest, they are parallel to each other, so they have the same length. So that means the question of how long the red line is compared to the blue one, the answer is this much. So this section is the path difference that we want. Only that small green section there is the path difference. The rest is approximately the same length. Okay? It's not exactly the same, but it's good enough, right? We are not wrong by much. So our task is just to find how long this green section is. Okay? So go back to this picture a little bit, right? Where we say the P is in terms of location can be characterized by an angle. And if I draw the line which is going through the center of the slit, like this, I want right at the center. Oh, okay. This is sometimes I don't like this application, but it's fine. So this is the center going through the center, going through number 0 here. The location of P, I can use this angle to tell where P is. Okay, so strictly speaking, it should be this line and this angle here. But again, because of this line very close to that line in terms of being parallel, it doesn't matter which angle I use, it's going to be the same angle, right? So this is something that you probably need to think about it a little bit, right? The role of this angle is to locate P, right? So if you know the angle, you know where P is on the screen. So that's kind of like the whole point here. All right, so this angle, going back here, that angle is the same as this angle. So I use green one here. Oh, sometimes I'm just so annoyed by this. Okay, so that angle is this angle here. Again, you might say that that's not exactly the case. Again, I'm wrong by saying that these angles are the same, but I'm not wrong by much. Okay, so this is the approximation that we are okay with. So these two angles is the same as the angle that we have in this picture, which is, written down to locate where P is. So a different location for P, right, means different value for the angle theta. Right. Okay, so let's go back here. So once we know this angle, as a few like simple steps in geometry, gonna convince you that this angle is also theta. Right? It's not that difficult to confirm this. So I have then this right triangle, the yellow one, and I know this distance. So the green section is simply d times the sine of that angle. That's the path difference. That's the green section that I'm talking about here. Okay, the path difference, which is this section, from the geometry of this triangle is just small d sine theta. And how do we use path difference to tell whether it's constructive or destructive interference? Well, you see if this is equal to n times lambda, which is multiple of lambda, this is constructive interference. Okay, I just say con. Or you have half multiple of lambda, where you say this is destructive interference. So this is why you have another formula for the double slit, which is interference of light wave. So I'm going to write it again in this page because that probably makes more sense. So what do we do? When you ask, okay, at one particular point P here, once you decide where P is, you can write down what's the angle here, right? You can measure it. Maybe it's 1 degree here. So if P is further up, then this thing might be 2 degrees, 2 degrees or something like that. Okay. So no matter what P is, you can write down this angle, right? And the formula that you use to check whether P is constructive or destructive interference is D here, sine theta, this angle, equal to n lambda or half multiple of lambda. Again, I'm just repeating what I say in the previous page. And again, this is just the specific version of path difference equal to n lambda or path difference equal to half multiple of lambda. But this expression here only applies for light wave. Because remember, we need to do some approximation in terms of two lines being almost parallel to each other. This is true only for light wave. Okay? But PD equal to n lambda gives you constructive interference. That's true for every kind of wave. But for light wave, we can do addition approximation here. Okay? So this is actually this is pretty much what you need to know about the double slit interference. Is that when you know D, you know the angle theta, then you can calculate whether the interference is constructive or destructive. Okay. There's one more thing I want to say is that sometimes measuring the angle directly is not as convenient because, I mean, think about how you would measure the angle, right? So it's probably more convenient to measure the angle in a little bit indirect way. So let's introduce another, well, two more parameters. One is the y distance, which is the distance of point P to the center line. And we can also introduce the distance from the screen to the double slit L here, right? Which is a very natural thing to do because when you set up the actual experiment, you need to know how far away the screen is from the double slit. And usually L is going to be, like 1 meter, 2 meters, something like that. So if this is the case, right, you can see that the geometry of the angle that we introduced earlier says that tan of the angle is about y over L. Right. It's essentially this triangle here that we draw here. Again, we are a little bit wrong, but we are not wrong by much. And usually the angle here is very, very small. And because of that, if you take out your calculator and you calculate the value here, when the angle is very small, then sine of theta is very, very close to tan of theta. Again, if you don't believe me, take out your calculator and put in, 0.001 or something like that. And you see that sine of that angle and tan of that angle is very close, right? But one thing you need to remember is you need to use the radian as the unit. Okay, you need to use radian as unit, not degrees, because that's not going to work. So that being said, sine can also be approximated to be y over L. And we do this because we can rewrite this equation not in terms of the angle, but in terms of y and L, right? So you can just do a direct substitution and you say d times y over L equal to n lambda gives you constructive interference, or half multiple of lambda gives you destructive interference. So it's the same set of equation, but written in different set of variables. depending on what is given in the problems, but they are the same thing. Okay, so again, this is really nothing new in terms of physical concept here. All right. So in reality, or you can read it here, in reality, the intensity is a little bit dimmer when you go away from the center. It's just because, I mean, this point is actually further away from the slit, but that's not really important here. The important here is that close to the center, the pattern is very close to the ideal case which we have here. Okay? So actually that's it. Okay? That's all I want to say about the double slit experiment. We have probably a few minutes to the end of this session. Maybe it's a good time to ask you if you have any question regarding what we talk about today. Otherwise, I'll just let you go a little bit earlier than usual, because this is it. This is the end of the material for the midterm. Anything? Well, you can also ask again on Wednesday, okay? Because you probably need to review a few things. On Wednesday, I'm gonna do a quick review, a recap of the material that we have covered so far. It's quite a lot actually, and then I'm gonna spend some time doing, like sample problems. And then if you have some questions that you prepare, please come and do ask those questions, because I mean, in general, the way you learn physics is a little bit different from, other subject that you are maybe more used to, right? You listen to me talking, you look at the lecture, you probably think that you understand everything, but actually you probably get at best like half of what I say, because you have to look at the problems, the homework that I gave you, and then think about how you apply the knowledge that you see on the lecture into solving that kind of problems. Only that time you will see that, hey, maybe I don't really understand what's going on here. And during that time, you will try to question your understanding, rethink about what I say, what is presented in the lecture, and after that, you will get true understanding. Okay. So if you have time again before today, before the next lecture on Wednesday, try to look through, or even better, try to do the problem in the homework again, and see if you struggle with any concept, right? And then you can come and then ask, and then when you really understand it, then that should be that should make you well prepared for the midterm on Friday. Okay, so since it seems like you don't have any question right now, that's all I want to talk about for today. So I'll let you go early, and I will see you all on Wednesday. Okay, so take care everyone, and thank you for your attendance today, and I'll see you on Wednesday.